All right, let's pick up and try to finish out this problem. So what we have so far is we have this problem. I adjusted the dimensions. You'll have to use the correct ones. We went in, we started by going down the link here and down the link here, writing two equations. One equation for this link, the other equation for this link. Then we got ourselves all the way down here to the um, excuse me, we got ourselves all the way down to the point where we were able to, okay, so let me try to review this. We worked through the first link. Okay, so I'm going to use the highlight pen. I can take it all back off in a minute. We worked ourselves down this link. That is this set of equations. We got ourselves to the point where we're sitting here looking at this thinking to ourselves, well, I can't really go any further. I can get the velocity of b as a function of the rotational speed of this AB, but I don't know what the rotational speed is of AB. Then we went down this link. When we went down this link, we had a new set of equations. But what you see is some of those came across. The velocity of B came across and appeared here because B is on both links. So we worked this all the way down to the point where we were about right here, and I did not put in the velocity of B yet. Then I put the velocity B in there. When I did, we ended up with a big set of equations like this. The velocity C on the left-hand side is such that it's prescribed. Now, in my case, I made it 30 degrees. In your case, it's 45. You just go down here, and I had 30, so I had to put in 30 and 30. So I get this equation. Turns out there's only two unknowns, and believe it or not, luckily there's two equations. We solve for both. I put it in a matrix form. I always do this because to me I can turn over and use Octave or MATLAB to solve it. And we got these sets of numbers. Next thing we did, I'm just reviewing here, is I decided to draw this out in an actual CAD program. And instead of using the geometry, I just used the dimensions and found each of these dimensions. Now this was in the CAD program, but I didn't take a snapshot with that dimension on there. We worked out the fact that BC is a rigid body rotating about that point. We found the omega BC to be the same number as before. And from omega BC, from the fact that this rotates around this, means that that point we can determine because we know this distance. So doing that, we got, here, we've got the value or the velocity of B, which we didn't need to solve from previously. We could. Since this acts as a rigid link, B has the same velocity whether it's on this link or that link. So I could take the velocity of B, put back over here, take the dimension right here, and find omega AB. And we got the same value. Now, unfortunately for accelerations, uh, you can't use instant centers. So let's proceed now to making another page, taking the data we have and moving in and doing accelerations. So I'm going to take a quick pause and I'll come right back to you. All right, let's go ahead. I think what I'm going to do, create a new page. I'm going to take this copy, do a copy, come back off here. I'm just going to add a new page and I'm just going to drop it down here. Part 2. What I'm going to do, go back here and get the values off of here, and luckily now technically these things should have a K value approach stuck with them. So with that in mind, I'm going to do a control copy, control C for copying, go back over here, go back right here, and I'm going to just drop those values right there. Maybe I'll shrink them down a little bit. So no longer am I concerned too much about finding these because I've already found them. And omega AB, okay, now you have to remember our sequence. This is X, this is Y. So this is a positive rotation. It's right hand rule, positive rotation there. So as we go forward, what we realize is AB appears to be, here let's do it this way, appears to be rotating that way. CD, on the other hand, appears to be rotating this way. Makes sense because this point's coming down while this point is moving away. So let's take a look as we start progressing here into the next phase of this. Okay, let me adjust my computer here for a second. And I'll just go in. I guess I'll use a blue. I guess that's fine. I don't know. Okay, so now what we've got, acceleration. I don't know. Let's go. We have the acceleration of B equals the acceleration of B relative to A plus the acceleration of A. Now let's focus on this step. What we're just focusing on is this link right here. As we focus in on this step, we do know this value. We also know for this particular link that that value is in fact 0. So the acceleration of B is equal to the acceleration of B relative to A. So this is if you're sitting on A, looking out there. Here you are sitting on A, looking out there at B. All you see it doing is rotating around you. So when you're rotating, you've got two types of acceleration. Oops. Let me move it up here. Alpha of the link AB cross, which is a vector, or B to A, which is another vector. Now in the text you'll find a couple ways of doing this. I'll list it one way as a vector crossed omega AB cross RB to A. Now as it turns out in the book, that's a plus, okay. Turns out in the book, this term, if you look real close, can be rewritten as omega, the magnitude of this vector, which is pretty easy to do because all of them are rotating in the z direction. And so you just got a scalar and a scalar component times that, times R B to A. Now, why is that? I can take a quick look back, but we talked about it in class. If you take, say, an object, let's say a disk, that is rotating, here's your disk, and let's say it's rotating in this direction. So as it turns out, omega cross R is the velocity. So this is the tangential, and so this is nothing more than v squared over r is the same thing as this omega squared times r. So as it turns out, you look in the book, you'll find out that this equivalency is talked about. We talked about it in class that day. So you're sitting here looking at this, and you're sitting here saying, well, I got two components. Now what we're going to do is focus on these two. Acceleration of B. So in fact, this one is exactly the same thing as that one. There's really not much of any difference. Actually, there's no difference. So let's carry this out. First, now I'm going to redo this because, okay, I need to go back to my other page. And I guess I should have copied, okay, 5 up and 3. So I need to go in here. Was it 5 up? No, it was 3. And this is 5. So I'm changing the problem. You will have to change it back. It was 1 there, so I made this 1. I made that 10. I made this 30. And I think I kept these. Yeah, so here's my adjusted problem. Okay, so now in my problem, I have to find a vector which points here. That vector is called R, vector drawn to B relative to A. That's pretty simple. That's 5I plus 3J. So there's that one. Okay, so we're going to need that right here. We're going to need that right here. I don't have alpha. I do know that I need to find it, but here's the key. I don't know what it is. So let's take a look at this. What we'll have is I, J, and K, 0, 0, alpha AB, whatever that number happens to be, 5, 3, and 0, and you're done there. Then the omega, and I did make a mistake here. This should be a squared. That should be squared. So my omega, what was my omega? AB was 6.66. Then square it times the vector. Okay, I don't know how to do it except 5I plus 3J. And go back, put in acceleration of B. I should be putting that with a vector across the top of it. So what do I end up with? Hang on. I can go ahead and break the cofactor expansion. Take this part out here. Minus J. And in this one I'll take this and this out, and it'll go there. 0, 5. And then I go ahead and do it, but this is going to be 0. Now, I'm going to have to, hang on. I'm looking for, nope, I'm looking for, oh. Now I forgot my numbers. 6.66 squared times 5 is 221.78. Yeah, let's see. Times 3. 133.07. Now, there's some things I can do here to check this along the way. Okay, so this would be minus 3 alpha AB I. That is a plus 5 alpha AB J minus 221.78 I minus 133.07 J. Now I'm going to see if I can find a way to check this out. Here's the way I'll do this. Okay, so I'm going to draw a link. Let's see. I believe, if I'm not mistaken, there's a way of drawing a background grid. Yeah, too many. Can I go even less? Okay, so what I'm going to do, here's what I'm going to do. Okay, so now I've got a background grid. Okay, so I go over 5 and up 3. So I start right here, go over 1, 2, 3, 4, 5, and up 3. So this is the scale, 5 and 3. Okay, first, I'll look at the acceleration, which should be, oh, that's a weird pen. Oh, okay. Which should be, that one's not so normal either. So this is the tangential. You actually should have a normal coming this way. So let's look at the tangential. If we've got a vector, which is this one, which is the vector here, r, drawn to, okay, here's A and here's B. B relative to A, 5I plus 3J. Now if I dot it with a vector that's normal to it, I should get nothing. So I should say R, BA, dotted with this portion right here. Okay, let's think about this. This is the tangential component. This is the normal component. Why? Well, they're separated here. This is the tangential. These two in green here, these are the normal. Okay, so go back in here and dot it with, just write in the vector minus 3 alpha AB I plus 5 alpha AB J. So if you take this vector and dot it with that vector, you'll get 5 times, wait, let's just do it. 5, okay, minus 3 alpha AB plus 3 times 5 alpha AB, which is by definition equal to 0. The next thing is, how do you determine whether this vector is in exactly the same direction or the opposite direction? Here's what I mean. I have a vector that goes like this. I have another vector that goes like this. So I can take this vector, oops, okay, take this vector, move it here, it's 180 degrees, call it here's vector A and here's vector B. A dotted with B is going to be equal to magnitude A, magnitude B, cosine of 180. Okay, cosine starts up here, progresses down to here at 90, 180, 270, and then 360, or back where it was. So cosine 180, if you want to check, I mean, it's just going to pop you out a minus 1. So it would be the magnitude of A times the magnitude of B. So if I wanted to dot this, in other words, dot this one with that one, you're going to get, okay, I'll tell you what, let's just do it. We're just trying to double check whether these are on the same line. Another way to do it is look at it like this. Okay, I was going to dot this. Let's try a different way just to check. Another different way is, I got a vector that starts here, 1, 2, 3, 4, 5, moves out 5, moves up 3. Here's the vector. So for every x value, okay, if you want to look at the slope in an x and y plane, it's the rise over the run. So the other question is, both of these are negative, so they point, this is positive, the other two are negative, they point back that way. They should have the same ratio. The x value $221.78. Here was the x value here. Take the 133.07. Let's divide those and let's see. Okay, so if I multiply that times 2, it'll be 6/10 or 0.6. Does this equal to 0.6? That's a good question. 133.07. 133.07 divided by 221.78. Oh, what happened here? 221.78. So not too surprisingly, it gives me that rise over run, or 0.6. So in fact, that's probably a better way of looking at it. This was a check. Okay, what I just did here was kind of checking to make sure that the answers I got made sense. In essence, here's what you've got. 1, 2, 3, 4, 5, and 1, 2, 3. You've got this item spinning here. This is A. You have a component of acceleration, which is tangential, which is this component, and you have a component of acceleration, which is the centrifugal part, which is this component. But, okay, those are explanations to kind of back up, you know, how you go about it and the interpretation of the results. We're still not finished. We do have numbers, actual numbers right here. Why? Because we know the rotational speed. We don't have numbers here yet. Okay, so we have to be patient and say I don't have those numbers. But what I do know is here, I'll write it out. I do know the acceleration of B is in fact equal to minus 3 alpha AB I plus 5 alpha AB J, and all I'm doing is recopying that equation, minus 221.78 I minus 133.07 J. Okay, I have that part solved. I can't solve that or that yet, or this. But here's what happens next. If you go in here and just say, here's what I'll do. Wait a minute, all of these are associated with that. So I'm going to take all of that oops. Well, I'll tell you what I'll do instead. I'll take all of this. I'll take my picture. I'll do a copy. Go back down to about right here. Paste the thing. Move it up to about right here. Let's make it a touch bigger. Okay. So at this point, I have an equation for the acceleration of b. What's the next step? Well, the acceleration of c is equal to the acceleration of c relative to b plus the acceleration of b. And that's where this is going to come into play. And believe it or not, I've got the acceleration of c right there, so I just have to work this intermediate detail out. So I'm going to take a break, go get a drink, and be right back. All right, we're back. Now, let's take a look. See, I went to the next page, or I dropped down below in this page, drew it up. I'm looking at link BC. So in this link BC here, we know B is common to both the previous link and this link. However, the relative accelerations are the ones we're going to take a quick look at. We already know AC, which we're going to do just like what we did before, but I'm going to postpone that to focus on this term, which is alpha BC cross R C relative to B minus the magnitude of omega BC, which we have from before and squared, so I don't forget the squared, R C relative to B plus, and we'll put that down later, acceleration of B. So each one of these terms, this is simply a copy. We know this value. We can figure this one. We can figure this one. We don't know this one. And we can figure this one. So each one of these terms is handled quite a bit different. So the first one I'm going to handle is, I'm going to handle these two first. So I'm going to focus on these two. So as a result, I'm just going to carry the AC straight down, equals to I, J, and K. I don't know the value of the angular acceleration. I have no idea. Now, let's look at the term R, C relative to B. It's a vector that, like we have here, points this way. And so in my particular case, I go out 10 and I go down. Okay, I don't just go down 3, I go down 3 and 1, or 4J. I had better stop and jump back to the previous page to make sure I copied that correctly from the previous part of the test. Okay, so 10 minus 4, 10 minus 4. So just wanted to double check. I want to make sure I didn't make a mistake before. It's always possible. Easily possible. Okay, so I put a 10, put a minus 4, put a nothing. Now, here I'm going to go back to my black ink pen. No, I'll go to this one. Let's go back to, all right, hang on. What is Omega BC? Well, I copied it in the very top of this. Omega BC, BC. CB and BC, same thing. 5.832. Doesn't matter whether it's a minus sign or not. Why? Because I'm squaring it. Okay, 5.832. Is that right? No, just 8.3. I don't know where I got the 2 from. We square that term, and then we put in our vector, which is 10I minus 4j, and I'm just carrying down this term. Deal with it later. Next thing, I'm just going to carry down the acceleration c, deal with it later. I get an I. In the I, I'm looking at these terms. 0, minus 4, alpha BC, and 0. Minus, because it's cofactor expansion. Here I'm looking at this one and this one together to give me that. 0 minus, oh, where am I putting minus 10 there for? 10 alpha BC and 0. I'm not even going to write the k because the cofactor component of the determinant is that, and it's a 0. So I'm going to start dropping that term. Minus, okay. I guess I better start going ahead and putting the terms together. 5.83. Okay, 5.83 squared times, you know what I'm going to do? I'm going to create an actual vector here. And that vector is going to have 10 and a minus 4 in it. 10 minus 4. So I get a 339, 89, and 339, 89, I, and I get a minus. Now see, I got to be careful here. Have a minus here, but I have a minus here. So the minus gets carried across. The next term is a plus, and I've already forgotten the number. 135.96. 135.96 J. And you can't forget the acceleration of B. Deal with it later. We're going to copy this in later. Now I've got to go ahead and break each of these down. Okay, plus these two minus these two becomes, well, there's a minus of a minus, 4 alpha BC I, plus these two minus those two gives me a minus. A minus gives me 10 alpha BCJ. And here's what I'm going to do. I'm going to make use of copy paste tab. Instead of writing the whole thing again, I can spend the time to do that though. Alright. Now, I'm going to make use of that again. Interestingly enough, here's how I'm going to make use of it. Copy and then paste. But this next one, so I copied it down. The next one, I'm going to go in. I'm going to take off that and put the acceleration of b in there. Look at this dot here and this dot here. Let's see if I can do a decent job of selecting this. Uh-oh. Tell you what, if you just do that, you don't, oh, wait a minute. I don't know what happened there. Try it again. Copy. Okay. Now I'm going to head down here and out to here and sort of drop my spot somewhere out in here. Uh-oh. Oh no. I'm sure I can move it down there somehow. There we go. So all I did is I went up, I grabbed the acceleration B, just copied the equation and dropped it there. I'll try to move it a little bit closer. Okay, so there's my terms. Now I've got to deal with the acceleration of C. Okay, the acceleration of C is actually not that difficult. It's actually a vector which has component going this way. Let me go back to this. Component running down 30 degrees, so I'm getting this straight off here. I'll try to zoom in on it so it's a little easier. So if we drew a line out here, this would be 30 degrees. This now is 10. So the acceleration of C as a vector becomes minus 10 cosine 30i minus 10, oops, that's supposed to be a sine, sine of 30j. Now, what I'll do, since I have everything written right there, I am going to try to move it down a little bit. Then what I'm going to do is interesting. I'm going to say we're going to go through, okay, we're going to go through this to get this. So the way I'll do that, I'll go ahead and erase this, do a copy and a paste, and sort of drop it right there. So with that, I don't know why it does this. With that, there's the equation. Big, long, stinking, nasty equation which occupies the whole page. However, let's identify blue as being the x-coordinate. Everything that's a coefficient associated with I look at all this. And everything that's green is going to be associated with a j. Now, all I got to do is pull out the green equation and the blue equation. And so let's start with the green equation. I'm sorry. Well, let's start with the blue equation. Minus, here. Let's make it a little heavier. So minus, well, still not that heavy, but I don't get why that is the way it is. Maybe it's the type of tool. Try that. Minus 10 cosine 30 equals to 4 alpha BC minus 339.89 minus 3 alpha AB minus 221.78, and that's it. It's not like that's not enough. This is the I equation, by the way. And the green or the blue equation. Okay, let's try to see if I can adjust that too. So the J equation. Oops, sorry about that. The J equation. Okay, hang on. Take a quick pause and finish the J equation in a second. Okay. Now we're picking up the green. Alpha BC plus plus 5 alpha AB minus 133.07. Now, I'm going to focus first on making the matrix because that will be the easiest part. So what I'll do is get these two components, put a 4 and a 10. So this will be the I equation, this will be the J equation, and then I'll get a minus 3 and a 5. Now we have to remember these numbers will change sign as I move them to the other side of the equation. 10 cosine 30 minus 10 sine of 30. Changing signs on the upper one, plus 339.89 and then plus 221.78 minus 35.96 plus 133.07. So what I think I'll do is move that to the top, try to get myself to octave, bring it out of full screen mode, bring this out of that mode, and and I'll try to create a K matrix, which is the matrix itself, 4, minus 3, 10, and 5. And then the right hand side is going to be, and I'll have to move it over, minus 10 cosine degree of 30. .89 plus 221.78 is 10 sine degree of 30 minus 135.96 plus 133.07. Close it all up. Uh-oh. And then what I'll do is invert K, multiply it times the right hand side, and I get 54 alpha BC is equal to 54.828, and alpha AB equals to minus 111.233. And if we look back at the actual test, oh, it's right here. Oh, I was supposed to find the velocity of B, so I found these two, found those two, didn't find the velocity of B yet, didn't find the acceleration of B. But those terms be pretty easy to come up with. They're buried. Let's go deal with the velocity of B first. The velocity of B can be extracted from the previous problem, and that is after I've determined what my omegas were, there is an equation up here in which the velocity of B looks like that. Okay, I am going to attempt the best I can to select that equation. We'll do a copy, and I'm going to move to the bottom of the page. I'm going to paste it right here, and then I'm going to say if I really want to find this, then that's not that difficult of a thing to find. The velocity of B would be equal to minus 3 times 6.66 I plus 5 times 6.66 J to be minus 19.98. I'm just going to say 20. So it's about minus 20 I plus 33.3. So that completes that one. Okay, If I want to know the acceleration of B, I can go to the part here, which is, here's what I should do. I should retitle these things. Here's what I'm going to do. Retitle this to acceleration, and retitle this thing to velocity. Alright, so I'm going to go back to the acceleration. What I'm going to do is I'm going to go over here till I find my term, which for some reason I did not write that. So here's what I'm going to do. I'm going to attempt to grab this one. We're going to see what I get. Copy. And I'm going to head off to the bottom. Drop it, say, right around here. Uh-oh. It dropped it right here. So maybe I can just drag it to the bottom. So now I can do the same thing, except I'm looking for this term to go here and here. And so what I'll do is minus 3 times minus 111,233 I plus 5 times 111.233 J minus 78 I J. All right. So I don't know. So let's see. Just go ahead and put this up near the top. Drop it out. So I can calculate it real quick using Octave. Minus 3 times minus 111.233 minus 221.78. That gives me the I component. And then the J component, 5 times a minus 111.233 minus 133.07. Woo. So I'm getting acceleration of somewhere in the neighborhood of 111.92 minus 689.23 and that's pretty much that. And so I think I've completed all this, so I think I'm going to go ahead and post this video and we'll go from here. Now remember, your problem is slightly, ever so slightly different than mine. Let's see. When I'm up here, I don't know how to change the pages. So I went ahead and adjusted mine to a 3 and a 5 and a 10 and a 1. So, but the sequence should be the same. You just replace the values of the x and y coordinates and the angle over here. So here, to further emphasize this, let's go look at what did I change. Here was the last part. I'm going to say I changed this dimension, I changed that dimension, change this dimension, that dimension, and this angle. I didn't change those. So we'll call it good. Hopefully that helps you progress through your stuff. The next 2 chapters are significantly easier than this. So just rest assured that after the spring break, things will be a little bit easier with regard to that. And stay well.